I'm gonna get started even though. Well, I'll go through the first few slides, and then once we hit a video, I'll go run and get my clicker like that. So, our second exam on chapters 15, 19, and 20 is on Monday. You get one sheet of notes. It'll be 75 questions. It'll be shorter than the previous exam. Chapter 20 homework is due on the 31st. The chapter 20 quiz is today. The chapter 16 homework is due on the 14th. So we are starting chapter 16 on the solar system, where we will contrast the geocentric and heliocentric models of the solar system. We'll talk about Kepler's 3 laws of planetary motion. We'll compute the period of revolution for a planet given its semi-major axis, its distance from the sun. We'll compare and contrast the terrestrial and Jovian planet characteristics. We'll differentiate between inferior and superior planets in the solar system. We'll provide evidence for the rotation and revolution of the Earth. We'll compare the atmospheres of the terrestrial planets, and we'll describe the general composition of the terrestrial planets. We'll describe what color produces the blue color on Uranus and Neptune, and we'll describe the eccentric orbit of Pluto. So astronomy is the scientific study of the universe beyond Earth's atmosphere. The universe is everything. It's all energy, matter, and space. The Milky Way is our galaxy, which is one of the 50 billion plus galaxies scattered throughout the universe. The solar system contains our sun, 8 planets, 5 dwarf planets, asteroids, comets, and meteoroids. And the sun supplies the energy for nearly all life on the planet Earth. Loaded, yes. So here's a short summary of the solar system, which is what this chapter will mostly focus on. I'll be back in a moment.
Our solar system is one of over 500 known solar systems in the entire Milky Way galaxy. The solar system came into being about 4.5 billion years ago when a cloud of interstellar gas and dust collapsed, resulting in a solar nebula, a swirling disk of material that collided to form the solar system. The solar system is located in the Milky Way's Orion star cluster. Only 15% of stars in the galaxy host planetary systems, and one of those stars is our own sun. Revolving around the sun are 8 planets. The planets are divided into 2 categories based on their composition: terrestrial and Jovian. Terrestrial planets, including Mercury, Venus, Earth, and Mars, are primarily made of rocky material. Their surfaces are solid, they don't have ring systems, they have very few or no moons, and they are relatively small. The smallest and closest to the Sun is Mercury, which has the shortest orbit in the solar system at about 3 Earth months. Venus is the hottest planet, with temperatures of up to 867 degrees Fahrenheit due to an atmosphere of carbon dioxide and extensive lava flows. Next to this world of fire is a world of water, Earth. The water systems on this planet help create the only known environment in the universe capable of sustaining life. The last of the terrestrial planets, Mars, might have also supported life about 3.7 billion years ago, when the planet had a watery surface and moist atmosphere. Beyond the 4 terrestrial planets of the inner solar system lie the Jovian planets of the outer solar system. The Jovian planets include gas giants Jupiter and Saturn, and ice giants Uranus and Neptune. The gas giants are predominantly made of helium and hydrogen, and the ice giants also contain rock, ice, and a liquid mixture of water, methane, and ammonia. All 4 Jovian planets have multiple moons, sport ring systems, have no solid surface, and are immense. The largest Jovian is also the largest planet in the solar system. Jupiter Jupiter. Nearby is Saturn, the solar system's second largest planet. Its signature rings are wide enough to fit between Earth and the Moon, but are barely a kilometer thick. Past Saturn are the ice giants Uranus and Neptune. The slightly bigger of these ice giants, Uranus, is famous for rotating on its side. Next to Uranus is Neptune, the outermost planet in the solar system and also one of the coldest. Orbiting the terrestrial planets is the asteroid belt, a flat disk of rocky objects full of remnants from the solar system's formation, from microscopic dust particles to the largest known object, the dwarf planet Ceres. Another disk of space debris lies much further out and orbits the Jovian planets, the icy Kuiper belt. Apart from asteroids, the Kuiper belt is also home to dwarf planets such as Pluto and is the birthplace of many comets. Beyond the Kuiper belt is the Oort cloud, a vast spherical collection of icy debris. It is considered the edge of the solar system since that is where the gravitational and physical influences of the sun end. Our solar system's particular configuration of planets and other celestial objects, all revolving around a life-giving star, make it a special place to call home.
So, much of the incoming solar radiation does not make it to Earth's surface due to atmospheric absorption. But various electromagnetic radiation from space, light, that will pass through Earth's atmosphere can be studied using ground-based detectors, otherwise known as telescopes. And in other regions of the electromagnetic spectrum, you have to use space-based instruments. So if you want to look at gamma rays or X-rays or ultraviolet or most of the infrared, you need to go into orbit because the atmosphere absorbs those wavelengths. So the Hubble Space Telescope is a good example of an instrument outside of Earth's atmosphere. And let's give this a second to load. Yeah, here's the Hubble. Okay, so it was just that. This is a short video about
Hubble is an upgradable space-based telescope orbiting at almost 600 kilometers, placing it well above most of our image-distorting atmosphere. It takes about 97 minutes to complete each orbit. It is designed to take high-resolution images and accurate spectra by concentrating starlight to form sharper images than are possible from the ground, where the atmospheric twinkling of the stars limits the clarity.
To gather as much light as possible from the faint objects it observes, any telescope needs the largest mirror it can get. Despite Hubble's relatively modest mirror diameter of 2.4 meters, it's well able to compete with ground-based telescopes having mirrors that are 10 or 20 times larger in collecting area. Hubble is a large satellite, about 16 meters long, or the size of a small bus. It's also one of the most complicated pieces of technology ever built. It contains over 3,000 sensors that continuously monitor the status of the hardware, so that technicians on the ground can keep an eye on what's happening. Time on Hubble is a precious commodity. Astronomers around the world regularly ask for much more time than is available. Keeping Hubble operating 24/7 is no small task. Not a second must be lost, and all operations, from observing to the so-called housekeeping tasks, such as repositioning the telescope or uploading new observing schedules, are meticulously planned. For astronomers, the most important components of Hubble are its scientific instruments. There are two groups of instruments in Hubble, here and here. The different instruments serve different purposes. Some are for making images. Some are designed to dissect the light from the stars and galaxies by spreading it out to form a rainbow-like spectrum. Hubble's unique vantage point in space makes it capable of observing the infrared and ultraviolet light that is otherwise filtered away by the atmosphere before it can reach telescopes on the ground. These forms of light reveal properties of celestial objects that are otherwise hidden from us. Some instruments, like ACS, the Advanced Camera for Surveys, are better for visible and ultraviolet observations. Some, like NICMOS, the Near-Infrared Camera and Multi-Object Spectrograph, are best for infrared observations.
Different mechanical and electrical components keep Hubble functioning. The power for Hubble comes from solar panels on the side which convert sunlight into electricity. Gyroscopes, star trackers and reaction wheels keep Hubble steady and pointing in the right direction, not too close to the Sun, Moon or Earth, as they would destroy the light-sensitive instruments, and accurately towards the objects being studied for hours or days at a time. Hubble has several communication antennae on its side that are necessary for sending observations and other data down to Earth. Hubble sends its data first to a satellite in the Tracking and Data Relay Satellite System, which then downlinks the signal to White Sands, New Mexico. The observations are sent from NASA in the United States to Europe, where they are stored in a huge data archive in Munich. No single nation could undertake such an enormous project. Hubble has been a major collaboration between NASA and ESA, the European Space Agency, from an early stage in its life. Hubble has been of paramount importance to European astronomy. European astronomers regularly win more than 15% of the observing time with Hubble, resulting in several thousand scientific publications over the years. Two groups of European specialists work with Hubble. There are 15 people from ESA currently working at the Space Telescope Science Institute in the USA, and 20 others make up the Space Telescope European Coordinating Facility in Munich, Germany.
It's always entertaining to see the Space Telescope Science Institute. Because that particular picture, you guys looking down across the street, the building they'd be looking down from is the physics building where I went to college. So I was across the street there most of the time. So the solar system is a complex system of masses held together by gravitational forces. The center, and by far the most dominant mass, is the sun. The sun is more than 99% of the mass of the solar system. Revolving around the sun, there are 8 major planets with, oh, that's out of date, over 250 moons. I'm going to have to go back and update some numbers in these slides. They just found even more moons around Saturn. So around Saturn? No, there's like 200. Like just recently they delivered another like 100 more found around Saturn. It's crazy. Jupiter has a lot, but Saturn has by far the most. The part of that is just they keep finding more there. It has to do with which planets have active orbiters around them. But I think Jupiter has one right now. Jupiter has like 70, 80. I think Jupiter has like 90 moons, but Saturn is now some ridiculous number. Uh, 274. It just this year it jumped up by like 100. So yeah, there's like 370 moons, 5 dwarf planets, and thousands of other objects. Asteroids, comets, meteoroids, etc. So the solar system, the original belief was in a geocentric model. The Earth was the center of the universe, everything orbited around. That's the intuitive understanding. Everything seems to be orbiting the Earth. The Earth seems to be still and everything seems to be going around it. The most detailed version of this, which was able to make the best predictions of the positions of the planets and things like that, was the one put together by Claudius Ptolemy in 140 CE. He built the most advanced version of this that handled the motion of the planets with cycles on cycles. And this held sway until about the 1500s. So the mid 1500s. The heliocentric model is a sun-centered model. And the first person to put together a real proposal for a sun-centered model with some actual heft behind it was Nicholas Copernicus, who lived from 1473 to 1543 and published his model like in 1543 or 1542 or something. He died almost immediately after publishing it. This just had a weird combination of bad timing. This geocentric model was supported by the church. And then this came up, the heliocentric model came up right around the same time as the Protestant Reformation. And so the church was jumping on everything around that time. But yeah, here's a short video about that. Is not the right video. I made a mistake. Oh well. Unhide slide. Delete this. Let me just quickly.
I'd do anything.
Pro plan? Excellent choice.
Yep, it keeps her ready for anything.
Let's show her.
If you watch the stars at night, it appears as if the stars are moving that the...
Oops. I got a mistake. Let me quickly fix this. Come on. I just need to set that up for the future.
Expressing my true self is powerful. I'm Jordan Childs, and I am a
Sorry
world-class
about the
gymnast.
ad.
Being in the fashion world, I've been able to...
If you watch the stars at night,
Here.
it appears as if the stars are moving that the Earth is completely still. This is an example of apparent daily motion and was used to justify that the Earth was the center of the universe for many years. Welcome to Moo Moo Math and Science and the geocentric and heliocentric models of the universe. From the perspective of the stars moving, it is very easy to assume that the Earth is at the center of the universe. This was the accepted theory called the geocentric model for many years. Great minds like Aristotle and Ptolemy proposed and supported this view of the universe. Geocentric means Earth-centered, and it just seemed right. However, there were some problems. For example, sometimes the planets appear to be going backwards or to have a retrograde motion. In order to explain this, small orbits called epicycles, which are orbits inside the orbit, were proposed to help explain this backwards motion. This model of the Earth being the center did not sit well with Copernicus, and in 1543 he proposed On the Revolutions of the Celestial Spheres, in which he explained what many had suspected, that the sun is at the center of the universe, and that we move on Earth along with the other planets around the sun. This is called the heliocentric model. He proposed that each orbit was a circle, and the Earth, like other planets, revolved around the Sun. This solved several problems, including the retrograde motion of the planets, arguing that such motion was only perceived or apparent rather than real. With the help of his telescope, Galileo Galilei discovered the moons of Jupiter and observed that small objects revolve around larger ones. Johannes Kepler proposed that the orbits of the planets were not perfect circles, but ellipses. Our planets travel in an ellipse and actually speed up when closer to the Sun and slow down when further away. The retrograde motion of the planets was explained because it is caused by the planets that move more quickly past other planets, and it appears that the planet is going backwards. Sir Isaac Newton proposed his laws of motion to help explain how objects interact with the world and each other, and his laws of gravity identified the responsible force behind celestial motion. We now know that the Sun is one of many stars and is not the actual center of the universe, but the planets do revolve around the Sun and not the other way around. If you'd like to know more about the movement of the Sun and planets, this playlist will help. Thanks for watching.
So, Johannes Kepler. Johannes Kepler took Copernicus's idea and data from Tycho Brahe, who had the best data of observations of the planets that existed at the time. And so he worked for Tycho Brahe for a while, and then when Tycho Brahe died, he absconded with his data, because Tycho Brahe was really secretive about his data. So Johannes Kepler was a German mathematician and astronomer who lived from 1571 to 1630. And he was able to work out a set of laws to describe the motion of the planets. And these laws, the first one is that the orbits of the planet, Kepler's first law is the law of elliptical orbits, which is that the orbits of the planets are not perfect circles. This is in some ways probably one of the most important steps that was taken. The rejection of circles solved the biggest problem with Copernicus's description, because Copernicus, just like Ptolemy, had to use circles on circles to describe motion. But Kepler rejected both circles and constant speed motion, and that solved that problem of the orbit, perfectly describing the orbits. So Kepler's first law is the law of elliptical orbits. All planets move in elliptical orbits around the Sun, with the Sun as one focus of the ellipse. So an ellipse is like a stretched circle. A circle is, in fact, a specific type of ellipse. An ellipse, it's symmetric about two unequal axes. It's defined as the set of all points where if you add up the distance from the two focuses, the total is always the same number. Like the circle is all the points that are a constant distance from one point. A circle is actually an ellipse where the two focuses are at the same point. So an ellipse is like a stretched circle. And it has two focuses. It has a major axis and a minor axis. And so for the orbit of a planet, the Sun will be at one focus, and the planet will travel around the ellipse. An ellipse has two foci, a major axis, which is the long way across, and half of that is the semi-major axis. And you can draw an ellipse by pitting 2 points in place and sketching around like this with a fixed length of thread, for example. And when we talk about an orbit, the semi-major axis is the average distance between the Earth and the Sun. For the Earth or for anything orbiting, the average distance between them and the Sun. Because the closest is this side of the focus and the longest is this side, and the average ends up being half of that total, the semi-major axis. So the average distance between the Earth and the Sun is an astronomical unit, which is 150 million kilometers, or 1.5 times 10 to the 8 kilometers. Kepler's second law is about how the speed changes as you orbit around the sun. So this is called the law of equal areas. Some imaginary line, if you draw a line from the sun to the planet orbiting, will sweep out equal areas in equal periods of time. What that means is that you travel faster when you're closer to the sun and slower when you're further from the sun. So here, area 1 and area 2 are equal in size, and you can see how, so they'll take the same amount of time to cover. You can see how you'll travel faster on this arc than you would on this arc. And the closest point to the sun is called perihelion. And for Earth, it's around January 4th. And the furthest point from the sun is aphelion. And for Earth, it's around July 5th. So yes, the Earth is closest to the sun in the winter. So perihelion is the closest point in the planet's orbit around the sun. This is the point where the speed is the fastest. For the Earth, which has a pretty circular orbit, this is 91,398,199 miles. And perihelion for Earth occurs around January 4th. Aphelion is the farthest point. That's 94,510,886 miles. That's the point in the planet's orbit furthest from the sun, where the speed is the slowest. Aphelion occurs around July 5th. Now, Kepler's third law is the way you can work out the relative time it takes for planets to orbit for different planets. So Kepler's first law and second law are talking about the orbit of one planet. Kepler's third law compares the orbits of various planets. And what it says, it's called the harmonic law. Kepler's third law says the period, that's how long it takes to go around the sun, in years squared equals the semi-major axis in astronomical units, Q. I mean, the general version of this is the period squared equals some constant. I don't know, we'll call it K, semi-major axis cubed. But if you use years for a period and astronomical units for A, that constant becomes 1. So that's what we're going to do in this class. So as an example, if something has an orbit with a semi-major axis of 5 astronomical units, the period squared will equal the semi-major axis cubed. So the period squared will equal 5 cubed. So the period squared will equal 125. Square root of 125 is 11.2. So that planet would have an orbit of around 11.2 years. That is close to Jupiter's numbers. Jupiter is actually a little bit different than that, but that's because it's not at exactly 5 astronomical units. So here is a short video about Kepler's laws.
Your personal finances start with you, but they support your entire home team. With Thrivent, your money can be a force for good for the people, causes, and communities you're most thankful for.
Sorry about the
Thrivent,
ad.
where money means more.
I thought this was kind of I'm gonna have to go through all of this.
Hello learners, this is Easy Engineering. Today we're going to talk about another fun topic in physics. It is all about the Kepler's laws of planetary motion. Kepler's laws of planetary motion are laws describing the motions of the planets in the solar system. They were derived by the German astronomer Johannes Kepler. There are 3 laws of planetary motion. Let us talk about them one by one. Kepler's first law of planetary motion, sometimes referred to as the laws of ellipsis can be stated as all planets move about the Sun in elliptical orbits, having the Sun as one of the foci. This means that planets are orbiting the Sun in a path described as an ellipse. This is a picture of an ellipse. Suppose this ellipse is where the planet Earth moves. The Earth moves along the ellipse around the Sun. The Sun is located at either one of foci of the ellipse. Now let us move on to the second law. Kepler's second law of planetary motion, sometimes referred to as the law of equal areas, can be stated as a radius vector joining any planet to the Sun sweeps out equal areas in equal lengths of time. The second law describes the speed at which any given planet will move while orbiting the Sun. Note that when a planet is close to the Sun, it moves fast, but when a planet is far from the Sun, it moves slowly. So if we draw an imaginary line of the movement of the planet and the Sun for every month of the year, we can see that when the planet is close to the Sun, it will form a wide but short triangle, and when the planet is far from the Sun, it will form a thin but long triangle. The Earth would have to adjust its movements in order to match the imaginary area. Did you know that the knowledge of Kepler's second law has proved the importance of Newton's law of gravitation? Newton showed that the motion of bodies subject to central gravitational force does not always follow the elliptical orbits as specified by the first law of Kepler, but instead, planets or other heavenly bodies can take paths defined by other open conic curves. Amazing, right? Now let us move on to the Kepler's planetary motion, sometimes referred to as the law of harmonies, can be stated as the squares of the sidereal periods of the planets are directly proportional to the cubes of their mean distances from the Sun. It compares the orbital period and radius of orbit of a planet to those of other planets. It is the ratio of the squares of the periods to the cubes of their average distances from the Sun is the same for every one of the planets. The comparison of each planet can be shown in this illustration. Now, what does that mean? Kepler's third law means how long a planet takes to go around the Sun, which is its period, is related to the planet's mean distance from the Sun. That is, the square of the period divided by the cube of the mean distance is equal to a constant. And for every planet, no matter what its period or distance, t squared over r cubed is the same number. And that's it. Did you enjoy our topic for today? I hope you certainly did. See you again next time for more interesting and fun topics only here in Easy Engineering. We make engineering topics easy and fun for you.
So here, let's say we have a planet whose orbit has a semi-major axis of 1.52 AU. That would be Mars. And we want to calculate what its period would be. Well, p squared, if we do everything in astronomical units and years, p squared equals a cubed, because the constant that was just mentioned in that video goes to 1. So p squared equals 1.52 AU cubed. 1.52 cubed is 3.51. We take the square root of both sides. We get the square root of 3.51. P equals 1.87 years. And that is how long Mars takes to orbit. So Mars orbits at a distance of 1.5 AU, and it orbits in a time of 1.87 years. Now, let's look at a planet whose orbit has a semi-major axis of 30 astronomical units. That would be Neptune. So period squared equals semi-major axis cubed. So p squared equals 30 AU cubed. So that's 27,000. And we take the square root of 27,000, and we get 164 years. And that's how long it takes Neptune to orbit. So you can do this for any planet, and you can work out what, if you know the semi-major axis, you can find the time it takes to orbit, and the opposite is also true. If you know the time it takes to orbit, you can figure out the semi-major axis. So the sun makes up the vast majority of our solar system, 99.8% of the solar system. Of the remaining 0.13%, Jupiter is about half. It's a little more than half. And Jupiter and Saturn together are over 75%. Planets with orbits smaller than Earth are classified as inferior. Planets with orbits larger than Earth are classified as superior. This is in the actual old meaning of those terms, where inferior means below, superior means above. So closer to the sun is below, further from the sun is above. That's how these are classified. This is not a very commonly used classification. All planets orbit the sun in a counterclockwise direction, as observed from above the North Pole. And every planet rotates as well in that same direction, counterclockwise, with two exceptions. Venus, which rotates very slowly backwards, and Uranus, which is tilted like 90 degrees and is basically rotating on its side. And it's technically tilted a little more than 90 degrees, and it's rotating a little bit backwards because of that. But it's basically on its side. So let's talk about the motion of the Earth, the two motions of Earth. Earth rotates around its axis. This gives us the day, and it revolves around the sun. This gives us the year. So rotation is spinning around your axis. Revolution is traveling around the sun.
Have you ever wondered about how Earth moves? Earth moves in two ways, rotation and revolution. Earth rotates counterclockwise on its axis, which is an imaginary line that runs through its center and passes through the north and south poles. It takes Earth 24 hours to make one spin. One complete spin of Earth on its axis is called a rotation. This is what creates days and nights. Early in the morning, the sun rises in the east. If you are at a beach on the Atlantic Ocean, you can see the sun appearing as if it is rising from the waters in the horizon. Earth is rotating so that this particular location is being exposed to the sun. When it begins spinning out of the sun's light, it appears that the sun is setting or slowly falling back down. This is the Earth spinning away from the sun's light. If you are at a beach on the Atlantic Ocean and the sun has set, then the sky becomes darker because Earth is rotating away from its light source. Earth rotates to face away from the sun for about 12 hours. It takes 24 hours for Earth to rotate on its axis, but it moves in another way as well. Earth follows a slightly elliptical path around the sun. One revolution around the sun takes 365 days on Earth. One full orbit around the sun is called a revolution. The exact amount of time it takes for Earth to make a complete orbit around the sun is actually 364 1/4 days. Since you can't have part of a day calculated into the calendar, leap years are created. A leap year happens every 4 years, when the year has one extra day added into the calendar. The day added every 4 years is always February 29th. So every 4 years, the month of February has 29 days instead of 28. This is a result of Earth's revolution around the sun. Earth's rotation and revolution are very important to us. Earth's movements on its axis and around the sun are what creates days, nights, and years for people on Earth. Rotation and revolution of Earth result in lightness and darkness, the seasons, and the length of day.
There was a mistake in there. It's 365 1/4 days, not 364 1/4. I don't know why they made that mistake. Now, a more common classification of the planets is by their type. There are two types of planets. There are terrestrial planets, which are like Earth, so we call them terrestrial. And there are Jovian planets, which are like Jupiter, so we call them Jovian, because Jupiter is the biggest one of them. The terrestrial planets are Mercury, Venus, Earth, and Mars. They have a high percentage of heavier elements, so they're generally smaller, denser, rockier. While the Jovian planets, Jupiter, Saturn, Uranus, and Neptune, have a high percentage of less massive gaseous elements. They're generally big balls of gas with liquid centers. They don't have solid surfaces. The pressure builds up enough for the gases to become liquid. So these are the terrestrial, the small rocky planets, and then the gas giants. Well, gas giants and ice giants will probably classify. Because Jupiter and Saturn are more similar to each other, and Uranus and Neptune are more similar to each other. So this is the solar system with the 8 major planets drawn to scale based on their size, with the sun behind. The distances between the planets is not to scale. Their size of the planets, but if the distances were to scale, they would stretch into the next state, I think. I mean, it would be really big because the distances between the planets are much bigger than the planets themselves. So let's start by talking about the Earth. The composition of the Earth, the atmosphere is about 21% oxygen, which is unique. It is the only planet in the solar system with significant oxygen in its atmosphere. Its crust is over 90% by volume. The rocks and minerals on the crust are also oxygen. So we live in an oxidized environment. So some examples of common minerals at the Earth's surface are quartz, silicon dioxide, calcite, CaCO3, that's calcium carbonate, feldspar, potassium, aluminum, silicon, Si3O8. So all the most common minerals have oxygen in them. So the Earth is not a perfect sphere. It's an oblate spheroid. What that means is that it's flattened at the poles and bulges at the equator. And that's because it's spinning. It's spinning, and that sort of pulls outward along the equators because of centrifugal force. And it bulges outward at the equator and is flattened a little at the poles. So the pole diameter is about 43 kilometers less than the equatorial diameter. This means gravity is stronger at the poles than at the equator. So the further north you go, the weaker gravity is, so the less you weigh. It's only like 1%, but it is real. So because the Earth has an average diameter of 12,900 kilometers, this difference is only a very small fraction. So there's also effect from spinning that is really the bigger effect that causes that gravitational change. But gravity is stronger at the poles than at the equator. Now, the fact that Earth is rotating around on its axis wasn't really generally accepted until the 19th century. This was very difficult to prove because we're on the Earth and everything is moving with us. So it's very hard to show that we're actually spinning and not everything else is moving around us. In 1851, an experiment was designed by the French engineer, Jean Foucault, and this is the Foucault pendulum, which is a very long pendulum with a heavy weight at the end. If you want to see one of these, the Museum of Science and Industry has 2. I mean, there's also one at Fermilab, but Fermilab is a ways away. But yeah, the Museum of Science and Industry has a couple of these that are nice. So it's a very long pendulum with a heavy weight at the end, and basically the pendulum will swing back and forth as the Earth moves underneath it. That's the general idea. And then depending where you are on Earth, that determines how fast it will rotate. So it won't rotate at all at the equator. It'll rotate in 24 hours at the poles. And in between, it will be a different amount. So around here, I think it's 36 hours. But yeah, the closer to the poles you are, the faster it will rotate. So here is a Foucault pendulum showing a proof of the Earth's rotation.
A Foucault pendulum is a pendulum with a specially designed pivot, designed so that it can swing back and forth in any direction around the vertical. So that's in contrast to, for example, a grandfather clock, where the pendulum has to swing in a particular plane. Let's imagine that you have a Foucault pendulum and you're at the North Pole of the Earth. When you set the pendulum swinging, you determine a plane in which the pendulum is swinging. And that plane is fixed. So as the Earth rotates underneath the plane of the pendulum swinging. And so if you now go back and imagine that you're standing on the Earth, you see the plane of the pendulum rotate every 24 hours. Now, as you go to lower latitudes away from the North Pole, the time that it takes the plane of the pendulum to rotate around lengthens. And in fact, at the equator, the plane doesn't rotate at all. At the latitude of Hanover, it takes 35 hours for the plane to rotate. So if you look at this pendulum here, if we look at it a few minutes from now, we won't even be able to detect that the plane of the pendulum swing has changed. But if you come back in an hour, you will definitely see that it's moved a little bit. And if you come back in 9 hours, this plane of this pendulum here will have rotated by 90 degrees, a very distinct change that you can easily see. Plane of the pendulum swing is also affected, for example, by the revolution of the Earth around the sun. And so, for example, if you have a Foucault pendulum at the North Pole of the Earth, not only will it rotate around every day because the Earth is rotating, but you will also get a much longer rotation over the period of a year from the revolution of the Earth around the sun. So if you think about it, this Foucault pendulum here is a kind of rotation meter. It's a way of measuring rotations. A suitably placed Foucault pendulum can be used to detect the rotation of the Earth, or the revolution of the Earth around the sun, or in principle, you could use a suitably oriented Foucault pendulum to measure the rotation, for example, of the solar system around the galaxy. So this brings up the question: the Foucault pendulum is sensitive to rotation, but rotation around what? And there's been a lot of speculation in physics and philosophy about that question. Ernst Mach, a 19th and 20th century physicist, put forward the conjecture that the Foucault pendulum is measuring rotation relative to the universe as a whole. It makes a kind of interesting connection between a local physics experiment here in this room and the universe as a whole. And the problem that people bring up is, how can this pendulum here somehow know something about the entire universe? So it remains as an unproven conjecture, more in the realm of philosophy than in physics at this point.
So yeah, if you'd like to see one of these Foucault pendulums, the Museum of Science and Industry has two. I was wrong about the time it takes to rotate. It's actually 42 hours at our latitude. At least I think so. And here is an actual time lapse of a Foucault
This video is sponsored by Brilliant.org. This is a really big pendulum, and unlike the pendulum in a clock, this Foucault pendulum at the University of Puget Sound is free to swing in any direction. It takes about 8 seconds for it to go from there over to here and back, but that's not the motion that I want to show you. Now, this is not an interactive exhibit, but I have special permission. The motion I want to show you is too slow for you to see, so I'm going to speed things up in this video, about 480 times, so that you only see the pendulum when it's at this point in its swing here. And doing that will compress the next 32 hours into 4 minutes of video. We're going to try science. Played back at this speed, the pendulum appears to move around the room. But that doesn't really grasp what's really happening, because the ground is what's moving. It's rotating. You are watching the world turn. Let me explain. The pendulum ticks back and forth due to the law of inertia, which states that an object in motion stays in motion, unless something acts on it. So the pendulum continues to swing along this plane of motion, and from its point of view, it's just swinging back and forth along that same plane. From the pendulum's point of view, the ground is what's moving. Now, while that's incredible if you ask me, it can also be hard to grasp, so I want you to picture this. A Foucault pendulum placed at the North Pole would appear to complete a clockwise circle once every 24 hours, as the Earth completes a day by rotating beneath it. But that isn't always the case, because at the poles, the relative rotation between a pendulum and the Earth's axis is at its maximum. So the closer you move a pendulum towards the equator, the longer it takes for a so-called pendulum day to take place. That's the amount of time it takes for a Foucault pendulum to move around the room, as it were. Here at the University of Puget Sound, a pendulum day is about 32.3 hours long. Now the reason it isn't 24 hours here is because the Earth is a sphere. So, the closer you put a pendulum to the equator, the further it is from the Earth's axis. And the greater the difference in angle between the Earth's axis and the plane that the pendulum is on. The greater that difference is, the less relative rotation there is between the pendulum and the Earth. So it takes at least 24 hours to see one pendulum day, and potentially much longer. You can actually figure out your latitude just by watching and timing a pendulum as it moves in this way, but of course there's easier ways to do that. It's now 5:30 in the morning, but I'm awake and ready to get back at it. At the equator, a pendulum day lasts forever. And that's because at that location, a pendulum is perpendicular to the axis of rotation. The planet and the pendulum's plane are not moving in relation to one another. Here in the northern hemisphere, Foucault pendulums rotate clockwise because of the Earth's rotation. And that rotation also causes sundial shadows to move clockwise. I mean, it's probably where we got the term clockwise in the first place. If we put a pendulum at the South Pole, it goes counterclockwise, but again, it takes 24 hours. We talk about the sun rising and setting, but that only appears to happen because of Earth's rotation. And up until this experiment was done, we could only assume that the Earth was spinning due to our observations of the sun, of the moon, and of the stars. But no one had figured out how to do an experiment to actually test that until 1851, when a physicist named Leon Foucault came up with this. And that provided the very first simple proof that the Earth rotates. He did all of that using nothing but a pendulum, and if you ask me, that is pretty remarkable. And that is a pendulum day. Now, it's worth noting that most Foucault pendulums on display, like this one, have an electromagnet at the top. But that's just to keep them going forever. You could just use a normal pendulum to do this experiment and get the same results. It just wouldn't last as long. And maybe that's a good thing, because this took me a long time. Making this video took math, engineering, physics, and a lot of effort. And I put in that effort so that I might inspire you to learn more about this incredible world around us. And that is why I've teamed up with Brilliant.org to help make that possible. Brilliant focuses on problem-based learning, and I really like that because I know that studies show that solving problems is one of the most effective ways to learn things. It's also just fun. Every day they release several daily problems in math, science, computer science, and engineering. And from those you can go deeper into an interactive course. And there's a recent daily problem on Brilliant that I really like about the physics of how to water your plants while you're away. And it turns out that there's a much simpler solution to that than building a robotic cactus watering machine like I did. So whether you want to learn more about the physics of everyday life, get better at math in ways that's actually useful, or just want to expand your horizons, go to brilliant.org/Curtis and finish your day a little
So, the Foucault pendulum provides experimental proof of the Earth's rotation. It doesn't rotate with reference to the fixed stars. And so the rate it rotates depends on latitude. And yeah, my first memory of it was correct. It does take 36 hours to rotate in Chicago. And my correction was wrong because AI lied to me. So that's an important lesson. Don't trust AI because it is dumb. So let's talk about the terrestrial planets. The terrestrial planets are Mercury, Venus, Earth, and Mars. Due to their physical and chemical characteristics, they're similar to Earth, so we call them terrestrial. There are differences between them. They all have somewhat different atmospheres, temperatures, etc. But they're all relatively small in size and composed of rocky minerals, material, and metals. They're relatively close together and close to the sun. They have no rings. They have few moons. Only Earth and Mars have moons, and Earth only has one, and Mars has two small ones. And only Earth has surface water and oxygen, but that's pretty much the same. Only Earth has surface water and oxygen in the whole solar system. So, Mercury is the closest planet to the sun. It has the shortest period of revolution. It only takes 88 days to travel around the sun and is the fastest moving. Its rotation is exactly 2/3 of its revolution. So it's about 55 days, I think, or something. It's 50 odd days. Yeah, it's 58 days or something like that. And it was named by the early Greeks after the Swiss messenger of the god because it pops in and out of vision pretty quickly. The temperatures on Mercury range from about 473 degrees Celsius on the side facing the sun hold on to heat. So when it's pointed at the sun, the side that's pointed at the sun gets warmed up a lot. And the side that's facing away from the sun loses all that heat very quickly. So it's big swings in temperature. Due to its small size and its closeness to the sun, Mercury has practically no atmosphere. And its density, its average density, is close to Earth. It's about the same as Earth's. The surface of Mercury was mapped by the Messenger spacecraft, which was the first spacecraft to orbit the planet. So Mercury is in many ways pretty similar to our moon. And here is a short video about Mercury.
The planet Mercury is named after the messenger of the Roman gods, because even
See if we can let this load a little bit more.
the ancients could see how swift and fleeting it is in the sky. But it wasn't until recently that scientists began unraveling Mercury's many mysteries. Mercury is the smallest planet in our solar system. Its diameter currently measures just over 3,000 miles, about the size of the continental United States. Like Earth, Mercury is a terrestrial planet with 3 main layers: a core, a mantle, and a crust. Only Mercury's crust has no tectonic plates. Also, its iron core is enormous by comparison, making up 85% of its radius, while Earth's inner and outer core account for just 55%. Because of the core's exceptional size, it's had a surprising influence on Mercury's overall size by causing it to shrink. The hot iron core has slowly cooled and contracted over the planet's 4.5 billion years. In doing so, it pulled Mercury's surface inward and has caused the planet to shrink radially by more than 4 miles. This shrinking planet is also the planet closest to the Sun, orbiting our solar system star at an average distance of roughly 36 million miles. Such proximity affects Mercury's atmosphere, or rather, the lack of one. It only has a very thin exosphere, which is traditionally the outermost layer of a planet's atmosphere. This exosphere is made of oxygen, sodium, hydrogen, helium, and potassium, all whipped up from the planet's surface by solar winds. The lack of atmosphere and close proximity to the Sun also makes Mercury a planet of extremes. The surface temperature can climb to 800 degrees Fahrenheit during the daytime and fall to 290 degrees below zero at night. Mercury's proximity to the Sun is also the reason behind its age-old reputation of being swift and fleeting. The Sun's gravity pulls harder on Mercury than any other planet, and like all planets, Mercury travels in an elliptical orbit, slowing down when it's farther away from the Sun and accelerating as it draws closer. Clocking in at an average speed of over 100,000 miles per hour, Mercury slings around the Sun in just 88 days. From Earth, Mercury is difficult to observe because it's fleeting and so close to the Sun. And so far, it's only been visited by 2 spacecraft, NASA's Mariner 10 and Messenger. Those missions gave us much of what we know today, but future ventures are in the works with high hopes of revealing more of Mercury's secrets.
So, Venus is the planet that gets closest to Earth. Its orbit is the closest to Earth's orbit. It's the 3rd brightest object in the sky after the Sun and the Moon because it's covered in thick clouds that are very reflective. So it's both close to Earth and the Sun, but also it reflects a lot of light. That's why it's so bright. And due to its brightness, it was named after Venus, the goddess of beauty. And the surface of Venus can't be seen from Earth due to the dense, thick clouds that cover the planet. Now, probes have been sent to the surface, but they didn't last long. But the primary way we look at the surface of Venus is by using wavelengths that pass through the clouds with radar. So radar images indicate the surface of Venus is composed of black hot rock from the Magellan. So the surface has been mapped by the Magellan orbiter. Most of the surface rocks appear to be volcanic. The Russians sent a handful of probes down, the Venera probes. The last one, Venera 13, I think it was 13, lasted the longest, but it only lasted 2 hours on the surface because Venus's surface is incredibly hot and incredibly high pressure. The air pressure at the surface is 90 times what it is on Earth. And the temperature is hot enough to melt lead. So Venus's atmosphere is very thick and composed of 96% carbon dioxide. It's so dense that the surface of Venus has a pressure of 90 atmospheres. And the large percent of carbon dioxide in the atmosphere results in very high surface temperatures due to what was a runaway greenhouse effect. So the surface temperatures are 477 degrees Celsius, so hot enough to melt lead. And radar images have revealed relatively few impact craters. There's indications of active volcanism. Most of these craters are fairly large because smaller incoming objects get burned up in the atmosphere. But there's also active volcanoes making these big oozing magma domes. Lava domes, sorry. So it's a terrestrial planet. This is a radar map of the surface. And this is a picture from the surface from one of the Venera landers. So this is from the Russian spacecraft Venera 13 that actually made it to the surface. So you can see it's basically volcanic rock. And the atmosphere rotates faster than the solid planet, but the planet, Venus has the slowest rotation of any planet. Its rotation is backwards and about the same length as its year. So here is a video about Venus. I don't know why these are putting so much focus.
Named after the ancient Roman goddess of beauty, Venus is known for its exceptional brightness in the night sky. But
for a moment.
behind this facade is a world of storms and infernos unlike anywhere else in the solar system. Venus, the second planet from the Sun, is very similar to Earth from a distance, but up close, it's a very different world. Venus is about the same size as Earth, just slightly smaller. Its structure is also nearly identical, with an iron core, a hot mantle, and a rocky crust. The crust of Venus, however, is dotted with thousands of volcanoes, including Maxwell Montes, a volcano almost as tall as Mount Everest. Venus also has a thick, layered atmosphere. It's full of clouds that rain sulfuric acid and whip around the planet at speeds up to 224 miles per hour, faster than some Category 5 hurricanes. The atmosphere is so thick that it creates a surface pressure similar to what it would be about half a mile deep in the Earth's oceans. This pressure is heavy enough that a human standing on Venus's surface would be crushed. The atmosphere is made of greenhouse gases, primarily carbon dioxide, which create an extreme case of global warming. They trap the sun's heat, causing surface temperatures to rise over 880 degrees Fahrenheit, making Venus the hottest planet in the solar system. Venus is so inhospitable, neither humans nor spacecraft are able to survive the planet's surface. But some scientists speculate that Venus wasn't always so unwelcoming. From roughly 2.9 billion to 715 million years ago, global temperatures on Venus may have been just a few degrees cooler than Earth's are today. And scientists theorize that the surface may have contained shallow oceans that could have held enough water to support life. Today, life may still exist in Venus's atmosphere. About 30 miles up in Venus's clouds, where the temperature and surface pressure are similar to those on the surface of Earth, scientists have observed strange dark streaks that appear to be absorbing ultraviolet radiation, a phenomenon that could be evidence of microbial life. Life may struggle to survive in the atmosphere of Venus, but it is this unforgiving environment that's made Venus an icon of beauty. It reflects 70% of all the sunlight that reaches the planet, which is why Venus shines more brightly than any other planet or star in the night sky. While more than 40 unmanned spacecraft have visited this infernal world, Venus, so illuminated in the darkness of space, still has much to reveal.
So that thing about possible life in the atmosphere, that those things they identified, turned out they were wrong. It wasn't biologically generated from photochemistry. Let's see. Well, I'll quickly read out about Mars, but Mars is the most visited other planet in the solar system. So Mars has a red color as viewed from Earth, and it was named after the Roman god of war. And the surface of Mars has two outstanding features that have intrigued scientists for decades. It has polar ice caps and extinct volcanoes. The ice caps are composed of frozen carbon dioxide in the winter and carbon dioxide vapor with frozen water in the summer. So there's frozen water at those ice caps always, and then there's also a layer of frozen carbon dioxide that builds up. And the surface of Mars is red due to iron oxide, fine grain iron oxide minerals. So the minerals had iron in them and oxidized to form iron oxides. So that's why they're covered in this red dust. Now, Mars is the most explored of the planets. So in 1997, pictures of the Martian surface were sent to Earth from a mobile radio-controlled rover, the Sojourner. In 2004, 2 more rovers, Spirit and Opportunity, landed on opposite sides of the planet and confirmed that Mars once had water at its surface. In 2005, the Mars Reconnaissance Orbiter was launched, and subsurface ice was found, and the amount of water in the polar ice caps was calculated. In 2012, the Curiosity rover carrying a mobile lab landed, and the goal is to see whether conditions have been suitable for microbial life and to search for past life. No life has been detected, but scientists are still working. There was a big announcement just recently that I have to look into about maybe there was evidence of past life on Mars or evidence of current life on Mars. Just like this year, like last month or something. In 2021, the Perseverance rover with the Ingenuity helicopter landed. So the Curiosity and Perseverance rovers that look like this are rovers currently exploring Mars, and Ingenuity was a helicopter able to fly in Mars's atmosphere. It outlived its planned life by a factor of about 12. No, more like 14, 13 or 14. It was supposed to do like 5 flights and it did 69. And then it landed badly and shattered its blades. So this is the Ingenuity, the helicopter. But we are out of time, so we're going to stop there. Remember, Monday is the test. So we'll be having the test on Monday. We will continue this on Wednesday next week. So I'll see you all on Monday for the test. Make sure you're here. It'll be shorter than the previous one. But yeah, have a nice day.